Okay, so in this section, we're not learning anything new, which is nice. We're just taking the concepts that we've learned with the properties of logs and to a certain extent the properties of exponents and solving, I guess, more complex equations. So far, we've done some equations where everything works out to be nice integers or simple fractions. Here, they're not going to be as nice, and there'll be an element of a domain restriction that throws another wrench into things. So we'll take a look first at the logarithmic equations, and to start off more simply, we'll keep the logs on one side of the equation. So this is more where you're going to have to apply a property of logs that might help you solve some things. So the first one is hopefully pretty straightforward. You have 6 times the log equaling 12. The one thing we'll kind of get out of the way first is the domain. And hopefully you remember from previous sections that we focus on the value after the log. So in this case, the value x, whatever is after the log has to be positive. So the domain is simply x greater than 0. So when we check our answers, we want to make sure that the answer we get is positive, right? So it's almost like there could be extraneous solutions, and much like in extraneous solutions, you want to check to see if they actually keep the equation solvent. So with that in mind, we can solve this, and we're just basically using our properties. So remember, when we have the number in front of the log, that can be treated as an exponent. So you can write this as x to the 6th equals 12. And at this point, it's really just rewriting it in exponential form. There's nothing really fancy about this. It's just, sort of a review, I guess, of some simpler types of problems. And so we would have 4 to the 12th equals x to the 6th. Now, you wouldn't want to take 4 to the 12th and then take the 6th root of that. So what you can do is try to figure out one way to keep the exponent the same. And so 4 to the 12th, here's sort of a trick, can be written as 4 squared to the 6th, right? So 6 times 2 is 12, and that's going to equal x to the 6th. So that might save you a little bit of time rather than taking 4 to the 12th and getting a really big number and taking the 6th root of that. I suppose you could do that on your calculator and it'd be the same thing. But what we can do here in sort of a more efficient way is realize that 4 squared is 16. 16 to the 6th equals x to the 6th. So it's sort of a different way of looking at the bases being the same. Here we're trying to keep the exponents the same. And it turns out then, of course, that x has to equal 16. But you could certainly put this in your calculator. And if you do that, you could take 4 to the 12th. It's going to be a really big number. 4 to the 12th is going to be that, 16 million number. And then if you want to take the 6th root of that, you could take the 6th root. Oh, wait, can I do 6? How about that? 6th root of 167777216, and we can hope that it's going to be a whole number. And in this case, it is. It may not always be, though, so just be mindful of that. Okay? So that's one way to do it. The second one, sort of the same idea, but you have a different, you have an issue with the domain restriction. And so here, we want to focus on the fact that what's after the log has to be greater than 0. So if you set that as a quadratic, we basically are saying that x squared minus 6x has to be greater than 0. We'll treat this like an equation, right? So if you just take x squared minus 6x equals 0, you can factor that, x times x minus 6. Now the question is, where is that graph going to be positive? So really, we're taking the x, making sure that that's greater than 0, and then x minus 6. So you want to look at basically this function. And this graph is a parabola with roots at 0 and 6. And so here are sort of your cutoff values of 0 and 6. And you want to figure out where the graph is going to be positive. So it takes a little bit of maybe thinking about the situation. X squared is a positive value, so this is going to be a positive quadratic, right? So if it's a positive quadratic, it's going to open up, which means it's greater than 0 here and here, right? The graph is above the x-axis for these intervals. And so you want to look at values that are x is less than 0, makes the graph positive, and x is greater than 6, makes the values positive, right? So think of those as test points. if you picked a point between 0 and 6 and plugged it in, let's say 3, you would have 3 squared minus 6 times 3. Well, that's 9 minus 18, that's negative. So it can't be in this area. So this is sort of an improper area because it's not greater than 0. So your answer has to be a value less than 0 or a value greater than 6, right? And so that's one of the things that domain restriction is going to remind you of, okay? So if you get an answer when you solve this that's like 2 or 3, then that's going to be an extraneous solution. All right, so solving this is the same way we would solve all the other questions from previous sections. 2 to the 4th equals x squared minus 6x. 2 to the 4th is 16. And then we have a quadratic that we can set equal to 0. And this is a nice, easy quadratic to factor. X minus 8, x plus 2. So x equals 8, x equals negative 2. Both of those are in our domain restriction, so we're good. 8 is greater than 6, and negative 2 is less than 0, so both of these answers are valid. Now, what you could do, if you didn't want to sit here and figure out the quadratic restrictions for the domain, is just take your answer and just plug it back into the original function. So if you plugged in 8 and negative 2, you would get a valid answer, all right? And we'll see some problems a little bit later where there will be some extraneous solutions. Okay? A little foreshadowing, here's that example, right? So you have log base 2 of 4 plus 2 log 2 of x minus 6 equals 4. So the thing that you might recognize right away is that this can be simplified to 2, right? So if we do that, we can have 2, and then we have the rest of our equation. And then we can write the 2 here as an exponent, log base 2 of x minus 6 squared. And then subtract the 2. Log base 2 of x minus 6 squared equals 2. Right, so if you write this in exponential form, 2 squared equals x minus 6 squared. And then you can solve that. 4 equals x minus 6 squared. And take the square root, right? Plus or minus 2 equals x minus 6, right? Take plus or minus square root of that, square root of that. So when you solve this, it's x plus 2 and 6 plus 2, or 6 minus 2. So we have answers of 8 and 4. And you might think, okay, those are my 2 answers. But keep in mind the domain restriction. Now, I purposely didn't do the domain restriction ahead of time because I wanted to see what happens. If you just blindly put x equals 8 and 4 in your answer, well, then be careful, because if you plug 4 into x, you're going to get the log base 2 of a negative number, and you can't have that, right? And so that's why we sort of look at the domain ahead of time, just to kind of reassure us. But if you don't show the domain ahead of time, please be sure to check the solutions, all right? And so because x minus 6 is in parentheses, that's what we want to make sure is our domain restriction. So x has to be greater than 6, and therefore 4 is an extraneous solution. Okay, so the only viable answer here is x equals 8. All right, so just keep that in mind. If the question doesn't ask for a domain, that's fine. Just make sure you check that solution to be sure. Okay, and so then finally, we'll kind of finish up with this example here using our properties of logs. We have a subtraction of 2 logs, and we have our negative 1. Now, before we get into this, let's take a look at the domain, because the domain's a little tricky. We have x squared plus x and x squared minus x. So much like we did in example B, we want to look at this as a quadratic. All right, so over here, I'm going to look at x squared plus x and set that equal to 0 and factor that. X times x plus 1. All right, so our solutions there are 0 and negative 1. So if we were to sketch a quick graph of that, we have a root at 0 and a root at negative 1. And again, it's a positive quadratic, so your graph is going to look sort of something like that. All right? Again, we want where those graphs are above the x-axis. So where is it positive? So in this case, x has to be less than negative 1 or greater than 0. right? So those are things we want to look out for in our answers, all right? Then we have to look at the second situation, x squared minus x equals 0. Again, factor it like you would, and your solutions are 0 and 1. So this graph looks very similar to the last graph. You have roots at 0 and 1, and it opens up, and so you have some sketch like that. Again, keeping in mind, all the values have to be above 0. So in this case, x has to be less than 0, or x is greater than 1. So now you've got to combine these domains to kind of see what overlaps. So here you have a situation where x has to be both greater than 0 and less than 0. Well, that can't happen. So we sort of have a situation where that doesn't exist. And so we sort of ignore that because there's no situation where x is both greater than 0 and less than 0. So the only restrictions we have are when x is less than -1 or greater than +1. All right? So you want to look at where there's an overlap and see what is the most restrictive domain. So we have a domain where x is both less than -1, well, not both, or greater than 1. All right? So our answers can't be between -1 and 1, right? Anything between -1 and 1 is considered below the y-axis, or below the x-axis there, and would be invalid solutions, right? So I think a little graphical display sort of gives an idea of where we're headed, okay? So with that, now we do our properties of logs. We have our subtraction of logs, and when we have subtraction of two logs, we divide. So we have log base 1/8, don't worry about that fractional base, and then you have the first term, x squared plus x, divided by x squared minus x, and that equals -1. Well, since we have one log with a base, we can rewrite this in exponential form. So that's sort of the focus of these 4 examples. When you have logs on just one side of the equation, ultimately you're going to rewrite it in exponential form. So 1/8 to the -1 equals that fraction. Now I think it's easier to rewrite 1/8 to the -1 as 8 to the +1, right? If you think about your negative exponents are reciprocals. 8 to the first is the same as 1/8 to the -1. And now you have your right side. And at this point, you can write it over 1 if you want, but you want to cross multiply. All right, and so you'll have 8 times x squared minus x equals 1 times x squared plus x. And at this point, you're just solving a quadratic. All right, and it's kind of nice because things will cancel a little bit and it'll be easy to factor. But we're taking basically your properties of logs and then ultimately adding some kind of algebraic / quadratic solving methods. Okay, so we distribute just like we would in any scenario there and solve for x. So it's probably easiest here to set it equal to 0. So I'll bring everything over and we have 7x squared minus 9x. Factor out an x. And we have our solutions, x equals 0 and x equals 9/7. Well, lo and behold, 9/7 is greater than 1, so that's valid. But x equals 0 is not less than -1 or greater than 1, so that ends up being an extraneous solution. So we only have one solution, and that's 9/7. Again, if you didn't solve for the domain, you could plug the 0 back in, and while it substitutes in here nicely, remember you can't have the log of anything equaling 0, right? The domain of any logarithm is always positive, so it can never equal 0. All right, so hopefully all those concepts, and if you think about a log graph, right, your basic logarithm graph looks like that. You always have your asymptote at x equals 0, so it can never equal 0. All right, so that's something to keep in mind as you're solving these. So these are a little bit more complicated in terms of having a domain or an extraneous solution affect it, but at the end of the day, these problems are all rewriting it in terms of exponential functions. In every scenario, we did that. It gets a little bit more involved when we have two logs. logs on each side of the equation. But don't worry, there's sort of a nice trick that we can get that we can use to make things a little bit easier. All right, so again, we want to look at the domain. The only value that has a variable is this one, so that keeps the domain simple. X is simply positive, no problem there. And I'm going to use my properties, and I'm going to have a 2 there, so I'm going to make log base 9 of x squared. And think of the negative as a negative 1, so log base 9 of 81 to the negative 1. Now you could write that 81 to the negative 1 as 1 over 81, which we'll do in a second, but the key is that since we have two sides of the equation with the same log base, through the properties of logs, we can effectively cancel them out. So when you have the same log base on either side and there's no other terms, you can just get rid of them and you're left with x squared equals 81 to the negative 1. That makes things a lot easier. So just because you see two logs, don't think, oh my gosh, this is going to be a harder problem. It may actually be easier. Now we can apply our negative exponent rule, make that 1 over 81, and take the square root, right? So the plus or minus square root of 1 over 81, which is plus or minus 1/9. Again, because x has to be positive, we ignore the negative sign, and so x is only equal to positive 1/9, okay? So there you go. That's not hopefully too bad. Okay, we just kind of extend that example with some constants. So this 5 might throw things off a little bit, but the idea then here, when you see a constant or some other term that's sort of ruining the situation, you can't just cancel the logs here because you have this 5. So you have to do something to deal with that 5. Well, that something is to move everything else to one side. So if you have a constant, just move everything over. Log 3 of x plus 19 plus log base 3 of x plus 1 equals 5. Well, you can combine these two logs into one log, right? When you add logs, you can multiply the pieces inside. Now, before I do that, I might want to look at the domain, okay? And so in this case, we have a scenario where x plus 19 has to be greater than 0, and x plus 1 has to be greater than 0. So x has to be greater than 19, and x has to be greater than negative 1. Well, you want to ask yourself, in which scenarios are both of these things possible? Like if I pick a number that's negative 10, that works here, but doesn't work here. And if you plug in negative 10 here, of course, you'll get a negative answer. So you want to look at the most restrictive domain, and that's the case where x is strictly greater than negative 1. So while these are both domain restrictions, they have to happen to both scenarios. And so x greater than negative 1 is sort of embedded into this domain, and so we effectively ignore that one, and we only have negative 1. Okay, so the idea is it has to be applicable to both logs, and a value that's less than negative 1 will work here, but not here. So you have to make sure it works for both scenarios. Okay, again, worst case, you can always plug in your answers at the end and see which ones work. Okay, so getting back to the log, since we're adding them, that means we can take each piece, x plus 19, and multiply it. Now, don't get too crazy yet. Oops, I forgot the 3 there. There's a little 3 there, base. Eventually, we're going to multiply this out, but we're not going to do it yet. First, since we have one log now, we're sort of like that first set of examples, we can write this as 3 to the 5th equals this set of factors. And here's where you want to multiply it out. And it'll work out where you can factor it, so it's not a big deal. But you want to make sure you get the logs to one side, which allows you to use your properties and then rewrite it as exponential, right? So bottom line is a lot of these examples will end up being an exponential equation if you can use the right properties of logs, okay? So 3 to the 5th is 243. Multiply out the set here, x squared plus 20x plus 19, set it equal to 0, subtract 243, which is negative 224, and believe it or not, this will factor. Might take a little bit of time, but there are factors of negative 224 that give you 20. Maybe you want to try splitting the middle, maybe you want to use quadratic formula, whatever works, but when you're done, these two factors will work, x minus 8 and x plus 28. All right, so x has to equal 8, or x has to equal negative 28. Well, definitely negative 28 will not make these domain restrictions work, so that's going to be an extraneous solution. Okay, so 8 is the only viable answer. Okay, so the next couple examples are sort of variations on this, and so we'll kind of see the same sort of rules apply. Here we have another constant, right? This is not in parentheses, so that's sort of a separate thing. So you want to isolate that on one side and bring the logs together to one side. Domain-wise, we have greater than 0 and greater than 2, right? So x has to be greater than 0 for the first one, and x has to be greater than 2 for the second one. Which one is more restrictive? The x greater than 2 is more restrictive, because 1 doesn't work for that one, but it does work for this. So x has to be greater than 2. So keep that in mind when you're solving this function. All right, so I'm going to move the 2 over here to keep it positive, so I'll move this log over there. We have log base 10 of x. I'm just going to ignore the 10 for now. Minus log base 10 of the quantity x minus 2 equals 2. Again, we have subtraction, so we can divide our terms. X over x minus 2 equals 2. All right, so there's that property of logs from the last section, and now you can rewrite this in exponential, right? That's the idea. The base is 10, exponent is 2, and there's your fraction. And you can solve this like you did a previous example. 100 equals x over x minus 2. You can cross multiply that. 100 times x minus 2 equals x. Distribute and solve for x. So bring the x over to the left. You get 99x. The 200 becomes positive, and divide. And by just a little bit amount, this is just over 2, right? 200 over 99 is about 2.01 maybe, something like that. But it's greater than 2, so it's a perfectly acceptable solution. Okay? And then finally, we just have a bunch of logs, but don't worry because the properties of logs make things nice. On the left side, we have a subtraction of 2 logs. On the right side, we have a subtraction of 2 logs. So let's simplify them. So we have log base a of x minus 5 over x plus 4, and that's going to equal the log base a of x minus 1 over x plus 2. All right? So one thing to keep in mind is the domains. We have 4 different domain restrictions, minus 5 plus 4 minus 1 plus 2. The bottom line is that you want to pick the biggest number, right? In the last example, 2 was bigger than 0. The example before that, negative 1 was bigger than negative 19. And that's sort of the pattern that we're going with. And so in this case, of the 4 roots, you have a 5 root, you have a negative 4 root, you have a 1 root, you have a negative 2. 5 is the biggest number. So x has to be greater than 5 because by default, it becomes greater than all of these as well. So that's sort of a nice quick way to look at your domain restriction. All right, now we have 1 log on both sides. And like we did in the very first example, when we had 1 log on both sides, we can cancel it, right? The logs are gone, and now we just have 2 fractions equal to each other, which isn't that bad once you cross multiply, all right? So take the denominator of one, numerator of the other, vice versa, and multiply them out. X minus 5, x plus 2, x minus 1, x plus 4, and now it's just basic algebra. X squared minus 3x minus 10, x squared plus 3x minus 4. And it's nice, the x squareds cancel out. And you're left with I'll bring the 3x over there. I'll make that 6x. I'm going to add the 10, and never mind, I'll subtract the 4. So I'm going to add the 4 over there, and that's going to give me a -6. So x equals -1. Well, sadly, that's not greater than 5. So this is extraneous, and we have no real solution. Right? Because if you plug in -1 to here or here, you're going to get an impossible scenario. All right? So again, even if you don't get the domain restriction itself, plug in your answer that you do solve for and see if it works. Okay? So those are the logarithm types of problems. We'll end with the exponential sides of problems. And these are, again, a little bit more involved than your typical exponential problems, so you're not going to get nice, happy numbers that you did before. All right? But the rules apply, and the nice thing was, on the quiz and on previous sections, you want to get it so that the bases are the same. Well, these questions are going to be written purposely so that you can't get the same base. There's no way to get the same base out of 3 and 5. There's no way to get the same base out of E and 8. So what are you supposed to do? Well, here's the idea. All right? So you're still going to use your properties, but you're not going to get a nice, happy answer. All right. So the first example, you have 2 times 3 to the 4x. Well, mathematically, if you have 2 by itself being multiplied, you'd want to divide by 2. And so get rid of the 2. You have 3 to the 4x equals 5/2. Right? Sort of the idea behind this is you want to isolate the exponential term. Right? So if you get the exponential term by itself, now what? Well, this is an exponential function which all up till now you've been able to solve. Since we can't solve it exponentially nicely, we have to rewrite it in log form. So now you're going to write an exponential function in logarithmic form. And so log, your base is 3, it's going to have 5/2 after it, and remember the exponent always goes by itself. So the 4x is always going to be isolated, and it's going to work out nicely because that's the variable you're solving. So when you're solving for x, you simply divide by 4. And so your final answer is x equals log base 3 of 5/2 divided by 4. That is your exact answer. And they will ask you on MathXL and the assessments, what is the exact answer? This is the exact answer. Now the follow-up to that is they will ask you for an approximation. Well, okay, now you have to use your calculator and you can plug that in. Right? So if you have the log base, cancel, wrong one, alpha window, log base, base 3 of 5/2 divided by 4, right? So take that, divided by 4, and your answer is 0.2085. Right? Depends on how many decimal points they want you to round it to, but that's the idea. Okay, so they're going to ask you for both an exact answer, which is no decimals, obviously, and then a decimal approximation. And that's the idea. So really it's just algebra. You just have to be mindful of it. And so for the first time really ever, we're not going to leave it as an exponential function. We're going to leave it in a logarithmic form. Okay, and so the same idea here. If you think of this as log base e of 8, that's going to equal x minus 1. So maybe you think of that as ln, natural log of 8, equals x minus 1. And then solve for x. We'll just add the 1. ln of 8 plus 1. Now, please, under no circumstances, ln of 8 plus 1 does not equal ln of 9. Right? If you do that on the calculator, ln of 8 plus 1 is this number. ln of 9 is this number. They are not the same. Do not combine them. It's not in parentheses, okay? So this is how you're going to leave your answer. If it helps to write it as 1 plus ln of 8, so you don't get tempted to add the 8 and the 1, that's fine. Either one of these is correct. And now that we just found the answer out, that was 3.079, right? So 3.079 is your approximate answer. Okay? So these problems aren't actually that bad. You just have to solve for x and leave it as a non-decimal. All right? So that's when you have one exponential expression, and we'll end this section when you have two exponential expressions. Now, unlike logs, you can't just drop the log. It would be nice if you could take the two bases and somehow cancel them. But the bases will be specifically written so that they're not the same. You can't get the common base. So what are you supposed to do? Well, in this case, when you have two exponential functions, you can take the logs of both of them. So pick a log. I'll pick log base 10 because it's easier to write rather than log base 2 or log base 3. I'm going to keep it log base 10. And I'm effectively going to take the log of both sides. Right, as long as I do it to one side, I can do it to the other. And because of the properties of logs, I can now move my exponents down. All right, so the first step, I'll put that in parentheses, is to recognize, all right, I don't have a common base. What am I going to do? The only option you have is to take the logs of both sides. And hopefully that will remind you of all the properties of logs, and then we basically solve an algebraic expression. So the biggest thing you'll see is that you want to bring the exponent down in front, which we did here, and now it's sort of algebra. Don't be thrown off by the fact that we're dealing with logs. We're still going to treat them as variables in the sense that we want to, say, distribute a number, right? Log base 3 is a number, and so you can think of this as 2x times log base 3, or log base 10 of 3, plus 1 log base 3. I'm going to erase the 1 because it looks like an L. Right? So all I did is I distributed that log. Okay? Once you get rid of the parentheses, the whole goal is to get x by itself. So we have one term here, one term here, one term here. The only terms with logs should be on one side, and the things that don't have logs should be isolated. All right? So basically, I'm going to move this x term over to the left. All right? And so we're going to have x log 4, all right? X log 4 minus 2x log 3 equals log 3. Okay? Once we have the x's to one side, we want to factor out an x. It's somewhat like what we did with our inverse functions when we were having to solve for x and we had to move the x's to one side and factor. So the process is really pretty similar. So you have log base 4 minus 2 log 3 equals log 3. Now again, don't be thrown off by all these logs. These are just numbers. We don't want the decimal approximations yet. They're just left as log 4, 2 log 3, and log 3. Think of it as another variable. Think of it as the variable y if you want. Okay? And so then when x is factored out, you just divide. Log 3 over log 4 minus 2 log 3. And this works with any log base. So if you chose log base 2 or log base 8 or natural log, it's all going to give you the same thing, right? So the log base itself doesn't matter. It's did you get the numbers to go along with it. So these are the numbers that matter, 3, the 4, the 2, etc. And then they'll want an approximation with a decimal. And so if you go in your calculator and type that in, you just have to be careful of some of the fractions. We have log 3 divided by the quantity log 4 minus 2 log 3. And that's going to give you negative 1.355. Okay? Again, it didn't matter which log I used. I could have used natural log, and it would give me the same thing, right? So if I do the natural log of 4 minus 2 natural log of 3, I'm going to get the same result. So it doesn't matter what log you take in the beginning, because the answer is going to be the same. Okay? And so just to give you another practice problem with it, there's a problem here. Okay? And so this idea is, again, you're going to use your properties of logs, take the log of both sides, and then move the exponents in front. So the x goes in front here. The quantity 1 minus x goes here. Since you have parentheses, you can distribute this. So this left side stays the same. 1 log 3 minus x log 3. All right, you're just distributing. And then so we have an x term here and an x term here. I want to bring that over. So I have x log 5 halves plus x log 3 equals log 3. And now we have to factor the x's. Right? X here, now we have log 5 halves plus log 3, and finally divide. So you have log 3 on top and that whole mess in parentheses on the bottom. So at the end of the day, it's just some nasty algebra, but don't let the word log throw you off, okay? And so when you plug that in your calculator, you would get an approximation, but there's your exact answer. The approximation is about 0.545. Okay? So hopefully those aren't too bad. It looks a lot more complicated than I think it really is. If you just keep your algebraic steps in your head, you should be okay. But definitely try the Math Excel problems because you will see these on the test.